much for the introduction, and I hope you had a nice lunch. And welcome to this talk about self-supervised deep learning towards autonomously learning machines. As you already heard, my name is Stiebellehner. I'm head of AI at Kraftwerks and also lecture at a couple of universities. And Kraftwerks, well, you might have heard about us. We are a Vienna-based artificial intelligence and big data company specializing in solving hard industrial problems using artificial intelligence and, of course, data. Also, most of our clients come from the industry, ranging from the automotive sector all the way to the energy sector and pretty much everything in between. The topic of this talk, self-supervised deep learning, is also primarily motivated by the work we do with our clients. Before we jump right into the topic, we first need to lose a few words about the current state of artificial intelligence, though. Probably, as most of you are aware of, AI has come a pretty long way in the last couple of years. In fact, we have made massive progress. For example, when you think of popular voice assistants such as Siri or Cortana, they have become incredibly good at understanding human natural language just in the last couple of years. Similarly, in a completely different area of artificial intelligence, in computer vision, we can now highly accurately segment even complex images into all of its parts. And not only that, we can even automatically generate text that describes what's happening in an image, so-called scene understanding. So obviously, great progress has been made when it comes to artificial intelligence just in the last years. And it turns out that many of these breakthroughs, many of these things you read about in the news are actually based on something that's called supervised deep learning. And this brings us to the first part of this talk, supervised deep learning, the good and the ugly. We will find out why supervised deep learning is so great and so many breakthroughs are based on it, but also we will get to know its very ugly side, one of its major downsides, one of its major weaknesses. Subsequently, we will find out how taking a self-supervised approach to deep learning can help us overcome or at least mitigate that core weakness. And finally, we will look into an industry case that hopefully gives you a good idea of how you can use self-supervision in practice to make your models better and more robust. But first, let's look into supervised learning. Probably some of you, or maybe even many of you, know this data set. It's an incredibly popular, famous data set even, containing images of, obviously, cats and dogs. And this data set is used by data scientists around the world to do their first steps in image classification using especially deep learning. So usually the task at hand is building a classifier that differentiates between cats and dogs based on images. Theoretically, you could approach this problem from two sides. You could approach it from an unsupervised side. Unsupervised learning, we do not use labels, right? And in supervised learning, this would be the other side. We do use labels. So we do use textual or numeric information that tells us if there really is a cat or if there really is a dog in that image. Just a quick recap to bring us all on the same page. In unsupervised learning, as I mentioned, we don't use labels. We just try to detect similarities and dissimilarities in these images, and based on that, form homogeneous clusters that hopefully, so we end up with a cat and a dog cluster. Of course, you're not using labels here. You lack supervision, so usually results will not be optimal. Actually, the weapon of choice for this kind of task really is supervised learning, especially supervised deep learning, because in supervised deep learning, by using different deep learning techniques, such as convolutional neural networks, we can actually teach them what makes a cat and what makes a dog, and they learn that in a fully automated fashion by providing them labels, by providing them ground truth, if there really is a cat or if there really is a dog in that image. And based on that, they then make the classification. And results can actually be astonishingly good, right? We can achieve human and even superhuman performance, especially for these types of tasks, which are very specific and also based on images. You can achieve astonishingly great results using supervised deep learning. But, well, that great performance that you often read about in the news, for reaching human level and superhuman level performance, very often you're going to need just tons of labeled data, and really tons. We are speaking about tens of thousands, hundreds of thousands, millions of labeled images. And that is a lot. And this is also a big, big problem. Because obviously, labeled data is so important for achieving this great performance, but at the same time, labeled data is scarce. Right? Data, we have a lot of it. We have data lakes and data warehouses full of data. But actually getting the labels that you need for solving your specific problem, that's something that's usually not existent. Of course, at that point, you could argue, well, you know, if I don't have these labels, I can just label it by myself. I can sit down on my desk, look through these images of cats and dogs, and note if there is a cat or a dog on that image. And I fully agree, yes, you can do that, absolutely. But you can imagine that this is quite some effort. And that effort rises very, very quickly with the complexity of the image. For example, this image is an image we took from a real practical use case we did together with Miba. Miba is a large manufacturer of industrial parts, and that image actually shows one of these parts. Well, on that image, in theory, you can recognize defects in the underlying part. Well, it's not that easy though, because these images, they are really large, they are highly noisy, and defects, they can be incredibly subtle, incredibly small. So it even takes a human expert quite some time to semi-reliably find and label, mark all these defects on such an image. So assume you want to automate that by training some supervised deep learning model. And for that, you need to build up a large labeled dataset of, let's say, 100,000 images, labeled images. You can imagine that that's going to be quite some effort. And you know, time is money, so it's also going to be expensive. How expensive? Well, it's actually not a too hard calculation to compute this. Assume you use some publicly available labeling tool, such as Amazon SageMaker Ground Truth, for example. They charge you, I think, if I remember correctly, around $4 per labeled image. Then, as we said before, you can do 30 images per hour, because you need 2 minutes per image. And then, of course, it's not going to be you labeling, but probably you're going to employ some working student, for example, that does the labeling. And that working student charges you $15 per hour. Well, and now, and this is critical, highly critical, but most people forget about that. You do not only need one person labeling your images. Why? Well, because a person can have a bad day. A person, you know, might just not be too accurate on that task. And this is actually the biggest problem. These images you saw are highly complex. These defects are so difficult to spot. It's really, really easy to oversee one. So you need multiple people labeling the same image, and then you need to aggregate these labels to actually end up with a really robustly labeled data set. If you don't do that, you're going to end up with a garbage data set. And you know how it is in machine learning, garbage in, garbage out. Your model is not going to learn accurately what you want it to learn. And if you do the maths behind this, you will find out that building up that labeled data set costs you 10,000 hours work time, and that amounts to more than $250,000 just labeling cost. And this is significant, right? Of course, if your business case is big, $250,000 might be nothing. You might not even lose a single thought on that. But for most companies and most departments, spending $250,000 on just building up a labeled data set it's a significant challenge, because at that point you haven't built a single classifier. At that point you haven't deployed anything in production. You basically haven't shown any value. And this is a problem. And this is why we argue that supervised learning, and especially supervised deep learning, is just very often not feasible. Because first, the labels you need to solve your problems probably don't exist. And second, if you want to create these labels, well, that's going to cost you a lot of money. And this is also why thought leaders of the fields argue that the AI revolution is not going to be based on supervised learning. And I agree, how can the AI revolution be based on supervised learning if we don't have labels, right? If labels are not ubiquitous, how can AI be ubiquitous? It can't, at least not when it's based on supervised learning. And when I thought about this the first time, I still found it a bit strange, because, well, deep learning is based on artificial neural networks. And neural networks, as the name already says, are inspired, at least inspired by the human brain. But we humans, we need so much less labeled data to learn a task highly accurately. So where did we go wrong here? What makes the difference? And this brings us to the core of this talk, self-supervised deep learning. When we talk about self-supervised deep learning, we first need to take a step back and think about the human brain. We need to ask ourselves, how do we humans actually learn? Do we do supervised learning? Well, absolutely, yes. Sometimes, for example, in school or at university, you have an explicit supervisor telling you what's right and what's wrong, what is a cat and what is a dog. So yes, we do. But of course, not always. You don't always have a supervisor standing next to you telling you what's good and what's bad. And even if we have a supervisor, for example, at school, you don't need to be taught something 10,000 times before you understand to do a task. Actually, just a few examples are sufficient. So again, we humans are such efficient and effective learners. Our supervised learning seems to be highly different from the supervised learning we do in machine learning, obviously. Well, how about trial and error learning or reinforcement learning? Just to bring us all on the same page, what is reinforcement learning? Basically, it's a subfield of machine learning where we try to teach an agent to learn a policy, a behavior to solve a highly complex, mostly sequential task, such as driving a car in a simulation or playing chess. And that agent learns that by, let's say, smart trial and error, basically. We humans, we also do trial and error learning, absolutely. Sometimes we try something, we fail, we try again, and then do better, hopefully. But of course, we don't trial and error everything. For example, you don't trial and error learning how to drive a car. You don't just drive around randomly until you manage to stay on the road, right? This is not a good strategy how you should learn how to drive. Actually, what we do is quite different. We get into a car the first time, and after a couple of hours, we are actually reasonable drivers. We can at least follow traffic in a basic way. And this is fascinating because if you want to teach a machine to follow real-world traffic in a reliable way, well, this is a big, big, big problem. You need a lot, not only of examples, but also engineering power behind this. For us humans, it's so easy. It's because we are such effective and efficient learners again. So obviously, also our trial and error learning that we humans do is fundamentally different from the trial and error learning we see in machine learning. So what makes us humans such effective learners? What is this magic ingredient that allows us to only require very little labeled data to learn a task incredibly well? Well, this magic ingredient is something that we call having a general understanding of the world. It's something that some also call common sense. We humans, we just know how things work, right? We just know how things work. And we obtain this general understanding through observation. From the day that we are born until the day we die, we humans, we observe. We observe what's happening around us with all our senses. We smell, we touch, we see, we hear. And this continuous observation, this taking the world around us as our supervisor, this is actually what forms our general understanding. And all this observation lets us understand the true meaning of things. What does it mean if something is heavy? What does it mean if something is hot? What are the implications? What are the consequences? Also, we start to understand abstract concepts and concept relationships, such as friendship, for example. And all this forms our general understanding. And this general understanding makes us such effective and efficient learners because this means everything we learn, we do not start from zero. We always have a head start. We always base everything we learn upon our understanding of how the world works and all our previously acquired knowledge. And this is what makes us humans such effective and efficient learners. Well, that's great for us humans, right? But this talk is not primarily about human intelligence, but of course it's about artificial intelligence. So the question remains, how do we inject this general understanding into machines? How do we make machines effective and efficient learners? How do we allow machines not to need tens of thousands, hundreds of thousands, millions of labeled data points anymore and still achieve great, maybe even human-level performance? Well, the answer is quite simple, actually. We just need to let them observe the world. We just need to make the data their supervisor. Well, but how do you do that? How do you force a machine to observe the world? Doesn't sound too easy. Well, imagine you put up a video camera at this traffic junction. And that video camera just continuously records what's happening in that traffic situation. So you basically end up with an endless video, an endless sequence of images. And now, imagine you have never seen a car before. You have never seen a motorcycle before. You have never seen traffic before. And somebody gives you this video, and you watch that video. I promise after a sufficiently long amount of time, you will have figured out what a car is, what a motorcycle is, and how traffic works. When is a car allowed to go right? When is a car allowed to go left? When it needs to stop, and so on. You have understood the concept of traffic by simple observation. Well, that's how we humans do it. But again, how do we frame this as a machine learning problem now? The good news is that supervised machine learning problems are always somewhat the same. They always have this very, very basic structure that you can see here. And I would say 95% of all supervised machine learning problems are framed just like that. You have some kind of input, which in our case, of course, is our video, our sequence of images. That goes into a model. Could be anything. In our case, that's, let's say, some type of neural network. That model spits out the prediction. And we then compare the prediction to the label, to the truth. Based on the difference, based on the error that our model makes, we're going to take a step in our optimization procedure, for example, using gradient descent. And the next time, our model is going to perform better. That's how supervised learning works at the very foundations. And it's quite clear what the user's input, and also the model part is clear. But what is our model going to predict, actually? And what are the labels? We don't have labels, right? We only have a video, only a sequence of images. So what should we actually teach our model to output? And this is actually where self-supervision comes in. And this is also where your creativity comes in. You need to think about, how do I shape and frame the data, the unlabeled data that I have, to form a supervised learning problem from it? One example would be, well, you could simply chop up your endless video, your endless sequence of images, into smaller subsequences, and always take the last image of such a subsequence and use it as label. And then teach your network to predict the future from the past. You teach it to predict the end of that sequence from the beginning or the previous elements of that sequence, of these images. Your model is going to learn to predict the future from the past. It's going to learn when a car is going to move, when it can drive forward, when it has to stop, when it's allowed to go left, and when it's allowed to go right. And we can do this in a fully automated fashion. You know, you can simply create a small Python program, for example, that chops up your video into small sequences, always takes the last frame of such a sequence, uses it as label, and then you train your network, and you're going to have an expert network when it comes to traffic, basically. And you can use this concept of self-supervision, of automatically creating labels from unlabeled data, also on other types of data. It's very flexible. For example, you can use it on images. You can just randomly crop out images of, let's say, faces, and teach a model to predict these rectangles. Or you can also use it on text. You randomly remove words from text and use the surrounding words, the context words, to predict the target word, the missing word that you removed. Well, that's awesome, but so what, right? What are you going to do with a model that predicts a missing rectangle in an image? That's usually not what you want to solve. And that's true. So what do we actually gain from this? What do we gain from a model that knows how to complete an incomplete phase? Well, what we gain from it is understanding. That model, by performing this task, by learning this task, builds up an understanding of the concept of a phase. It learns very low-level representations about the face, and also high-level representations, such as it's going to learn that usually there is one nose in a face, there are two ears in a face, these ears sit on the sides of your head, and so on. It will learn a general understanding of the concept of a face. And you can use this understanding, you can use this knowledge for any other task you really want to solve that is somewhat related. What does that mean? Well, first, let's say you do exactly what we did. You randomly remove rectangles from images of faces. And even if you have little images of faces, you can remove rectangles in a variety of different ways, right? So you can actually end up with a large data set. You train your model to predict these missing rectangles. Your model will then have an understanding of the concept of a face. Then you take the same model, you take the model with all of its knowledge and use it for whatever task you really want to solve. For example, for predicting the age based on images. You just fine-tune it a bit, maybe modify the architecture a bit, no big modifications, and your model is not going to give you the missing rectangle anymore, but it's going to give you the age of the person that's visible on that image. And all that by simply using a model that has acquired general understanding through self-supervision, and then you just fine-tune it with little labeled data for the task you really want to solve. What you gain from that is overall, well, first of all, since you're first building up general understanding and then fine-tuning your model to the task you want to solve, and that means your model will need less labeled data to achieve better performance. Your model will converge faster because its weights are already in a somewhat optimal position. And also your model is going to be more robust because the features it learned, these important characteristics, were learned on a very large data set, on your self-supervised data set. And you were just fine-tuning on your downstream task where you potentially have very little labeled data. So this is actually really a win-win situation here. But how does this work in practice? Is that really usable in practice? Well, and this is why I brought this industry case with me, which we did together with upstream mobility. And our task at hand was estimating mode of transport from GPS movement data. Well, GPS movement data is quite easily described. You just have sequences of GPS coordinates and an associated timestamp. And basically, what we got was a data set of these trips across Vienna. And that person here started his trip at the green dot, ended it at the red dot, and every dot in between was a GPS signal. Our task was for each of these GPS signals, estimate which mode of transport he was taking. Was he going by bus? Was he going by metro? Was he walking, cycling, going by car, and so on? Actually quite hard, quite complex, given the little information. So the first thing we asked ourselves here was, so how would we humans solve this problem? Well, what I would do is, I would go on Google Maps and check out where transport lines are running, right? Because if a GPS signal is nowhere close to a metro line, probably he was not going by metro. And that's what we did. We enriched this map of Vienna by adding image channels, and each image channel represents a different transport network. One represents the metro network, one the bus network, and so on. This is awful for humans, right? This produces an image you cannot interpret, but it is great when it comes to deep learning. Well, and then we used that information to embark on building a supervised deep learning model with no self-supervision at this point. The way we framed this problem was, well, we framed it as a sequence learning problem. Now, what does this mean? So basically, we thought, our hypothesis was, the movement history of a person provides us with important information also for estimating his current mode of transport. Because obviously, if a person has been on the metro for the last 5 GPS signals because his GPS signals were just on top of that metro line, and his current GPS signal is again on top of that metro line, it is quite likely that he is still on that metro. Because changing transport, modes of transport, is actually associated with costs in terms of time, effort, and maybe even money. So our hypothesis was we used the previous movement history to estimate his current mode of transport. So again, how do we frame this as a machine learning problem? We have a big image with dots on it, and then we want to incorporate a sequence of dots to make our estimation. So you can do this in a variety of ways, of course. The way we did it was, for each of these dots we want to incorporate for making our prediction, we cropped out a small rectangle of the image around it. So we end up with a sequence of image tiles. Each of these image tiles, representing the path in total, then goes into a convolutional neural network, a so-called CNN, which is a type of neural network that is very good at extracting important information from images. That CNN then produces what that CNN thinks is important for making the modality estimation, so-called feature vectors. It learns feature vectors, which is simply a numeric dense vector representation of that image and what is important in that small image tile. That sequence of feature vectors then goes into a recurrent neural network, a so-called RNN. And RNN, again, is a type of neural network, just a very different type, which is great for modeling sequences, for modeling temporal dependencies between elements of a sequence. And since we are dealing with a sequence of GPS coordinates here, or a sequence of image tiles, or actually now a sequence of learned image features, and RNN is an obvious choice here. And that RNN then finally gives you, in the end, which modality the person was likely to be taking. Was he walking, going by bus, taking the metro, and so on. And that, what you can see here, all that was basically one single deep learning model. And it worked out reasonably well, actually surprisingly well. However, you can imagine that this was not a small model. Actually, we were dealing with, I think, a bit more than 100,000 of parameters in that model, which is okay if you have sufficient labeled data. And you can guess, well, we didn't, of course. We were dealing with rather little real-world data here, which is a problem given if you use a large network, because a network is likely to overfit, and so on. So we thought about, well, how about self-supervised deep learning? This is actually a very good case for that. How about first letting the model develop general understanding, and then taking this model with all of its understanding and using it for solving our very specific modality estimation task. And that's how we came up with that concept. You could, for example, teach your model the entire Vienna transport network in a self-supervised pre-training stage, just as we did before, then take that model with all of its knowledge and fine-tune it to make modality estimation happen. Sounds good, but how do you teach a model the Vienna transport network? And this is again where it comes to self-supervision, where it comes to your creativity. How can you frame a problem from the data you have to make this happen? One way is to, for example, randomly sample 32 by 32 pixel tiles, again these small image tiles, from a map of Vienna, which is publicly available, of course. And then you just automatically check which line of transport is running on that tile. It's all information that's publicly available again. You take that as labels and you teach a model to predict which line of transport is running on a given image tile. Your model is going to learn the Vienna transport network. It's going to be an absolute expert. And you can then take this model, you can take this CNN that knows everything about the Vienna transport network and put it back into our original architecture, replacing the CNN from before, the CNN that had to be trained from scratch. Our model now does need to be trained from scratch. It has a big head start. It has acquired general understanding. So it just needs to be fine-tuned a bit. And that CNN then passes on high-quality feature vectors, again, to our RNN, which learns the temporal dependencies and outputs the predictions. What you gain from this is you have a significantly smaller model, because you do not need to train the CNN from scratch. This means you can have many of the parameters frozen, and you end up with a model with trainable parameters going from 100,000 before to 10 or tens of thousands now, which is a lot better suited for little labeled data. So again, what you're going to get is your model will be able to deal with little labeled data better. It's going to be more robust. It's going to converge faster because you simply have to optimize less parameters here. And overall, it's going to make more accurate predictions given the same labeled data. We have come a pretty long way now, all the way from supervised deep learning, why it's so great, so powerful, but also we got to know its ugly side. We got to know that it just needs tons of labeled data to achieve this famous performance. Subsequently, we found out how taking a self-supervised approach can help us overcome that key problem of supervised learning. And finally, we looked into the industry case that hopefully gave you a pretty good practical idea of how you can apply self-supervision to your problems to make your models work better on little labeled data. I hope you enjoyed the talk. Feel free to ask any question you might have. In case we are out of time for questions, I will be here after the talk as well. So feel free to approach me and ask any question in private that may have been left unanswered. Also, of course, drop me an email and add me on LinkedIn. I'm always happy for interesting messages I get. And most of all, visit our website, craftworks.ai. Thank you very much.
Okay, let's see. I think we maybe have time for one question. Would you like to choose which one do you think would be the best one that you'd like to answer?
Okay, I think the second one, what is the main difference between supervised and self-supervised learning? This is an important question because it's very fundamental. So self-supervised learning is supervised learning. The concept behind self-supervision is that you do not have a labeled data set, but you come up with a smart task how you can create labels from a previously unlabeled data set, not needing any human labeling. This is the concept of self-supervision. You use the data that you have, that video that we had before. You do not have any labels. You cannot just apply supervised learning because you don't have labels, but you need to implement a self-supervised task where you first pull out these labels to actually make supervised learning happen. And you're learning from a distribution that is within the data, actually.
Thank you. And for those who didn't get the questions answered, please feel free to see Simon in the hallway track after this. So once more, a round of applause, please. Thank you very much.
Thank you.